Hi everyone, welcome to Phys 3500, Classical Mechanics. I'm your instructor, Dr. TJ Hammond. This week we're going to be talking about Chapter 7, Hamilton's Principle, Lagrangian Hamiltonian Dynamics. We'll in fact be covering Chapter 7 for this week, next week, and the week after that, and then we'll be having our midterm the week after reading week, which is I think the week after that. So yeah, we'll be dedicating a lot of this course time to Chapter 7. That's going to be one of the main purposes of this course actually is to understand how to implement what we learned last week, which is calculus of variations, and implement that to actual physical problems using the Lagrangian. So we have to explain to you what the Lagrangian is, of course. Okay, so why are we covering this? So we want to introduce ourselves to a new way of solving dynamics mechanics. So the nice thing with Lagrangian Hamiltonian mechanics is we can use generalized coordinates. So although a lot of our problems, especially at the beginning, will still be using Cartesian and polar coordinates, so you won't quite see this benefit at the beginning. It's true that you can actually set up these problems with very general coordinates. And so that means that we're not restricted to polar coordinates like we were, or Cartesian coordinates like we were with Newtonian mechanics, which allows us for some extra flexibility. Also, the solves we end up setting up these equations of motion using energies, and as we get on later on, we'll see that symmetries also play an important role, but using energies and symmetries rather than forces and momenta. And it turns out that this is really important for solving quantum mechanics problems. So for those of you who remember like the Bohr atom derivation, he starts off with simple Newtonian forces and Coulomb charges and stuff like that. It turns out that how quantum mechanics are formulated with Schrödinger, they're actually solved based off of Hamiltonian mechanics. And so it's really important when we're solving quantum mechanics problems, we have to understand where these kind of ideas come from. So this week we're going to be covering the beginning of the chapter, sections 7.1 to 7.5. For the daily assignment, read and summarize section 7.1, the introduction, and 7.2, Hamilton's principle. So Hamilton's principle is extremely important. It is basically effectively like Hamilton's law for Lagrangian mechanics. As I say, it's on par with Newton's laws. So Newton's laws, you know how to state them, you know what they are. If you took 2500 with me last year, I made sure that you knew what they were. Hamilton's principle is as important as that for working with Hamiltonian and Lagrangian mechanics. Okay. So Newton's laws were developed by one person, of course, because of Newton, although, as he said, he stood on the shoulders of giants. And so, there are many other people before him who kind of inspired these ideas. But basically, he came up with everything kind of together. Oh yeah, and so the second point is any new formulation of mechanics, of course, requires us that we get the identical equations of motion. So we know how to solve a pendulum with Newton's laws. We, of course, if we set up a pendulum and solve it with Lagrangian or Hamiltonian mechanics, we, of course, have to get the same equations of motion. So this leads to a question, what are equations of motion? So when I say solve for the equations of motion, this is not to do with the textbook. This is something to do with when I ask you to, like when you're answering a problem, if I say, what are the equations of motion, understand what that means rather than solve for the trajectory of the particle. So the equations of motion are, like mx double dot equals whatever, something, because x double dot is the equation of motion. That's the acceleration of the particle. If I say solve for the trajectory, then you have to, solve for what x is. But just finding the equations of motion is just that differential equation. These formulations have to agree with and be verified by experiments, of course. So if we set up Newton's laws and we get an equation of motion, and if we set up Lagrangian mechanics and we get a different equation of motion, well, first of all, they have to be the same equation of motion because we know that Newton's laws have have been verified for everything that's bigger than about a fraction of a millimeter to something that's about the size of our solar system. Newton's laws work really, really, really well. They don't work on the size of a cosmos, like the size of a galaxy or something like that, because we need general relativity for that. But even general relativity kind of fails there. And they also don't work for something that's much smaller than, a thousandth of a millimeter or something that's smaller than a micron, because then we get into quantum mechanics. But for something that we can see kind of by eye, they work really, really well. And so these formulations for Lagrangian mechanics have to agree with Newtonian mechanics, and they both have to be, they have to agree with and can be verified by experiments. So Lagrangian mechanics are formulated in terms of Hamilton's principle, which is taking the extrema of a path, okay? And so that's why we were talking about the extrema of paths last week with the calculus of variations. So to get into Hamilton's principle, people knew about 2,000 years ago that minimizing the distance can explain some physical phenomena. So Hero of Alexandria, who was just after, 0 AD, uses this idea to derive the law of reflection. So we'll get into this derivation in class, but remember that the shortest path is a straight line, but if you have some light source here and you have something blocking here, but you have a mirror, then the shortest path that this light could possibly take comes here, hits this mirror, and comes back to B. And by saying that this is going to be the shortest path, then you get that the incident angle theta I is equal to the reflected angle theta R, which I'm sure you all know because you guys took second year optics, but I've also noticed how a mirror works before. So the thing is that this doesn't actually work for refraction, so your assignment will actually get into that. But Pierre de Fermat actually reformulated this idea from instead of least distance to least time around 1662. So Newton's Principia was actually 1687, so just to give you some historical context, that Pierre de Fermat was actually working at the same time as Newton. Of course, Pierre de Fermat was in France, whereas Newton was in England. But they're actually kind of contemporaries of each other. And so they could have been working on ideas at the same time. But these ideas of minimizing principles to explain physics were originated in optics, as I just said. This was to minimize the path of least time rather than path of least distance. So as I said, you probably have taken this in optics, but what is optics? So I am in optics. I like to work on lasers. And these are just kind of aside questions that we can discuss in lecture, but why would this formulation be useful for understanding quantum mechanics? So maybe think about that, and then we can discuss that in class. There's also this other French philosopher and scientist, Maupertuis, in 1744. So this is 80 years after. That instead of asserting this idea of least time, he asserted the principle of least action, where when he came up with this formulation or this formalism, this action thing happened to have units of distance times momentum or energy times time. So what else has these units? So distance times momentum would be, say, if you are applying, like if there's some momentum that's on on something that has like a long lever, and it has this distance lever arm R, and you're changing this, or you're giving this momentum P, then of course R cross P is equal to L, so that's angular momentum. But it turns out that there's a fundamental constant that actually also has the units of distance times momentum, or energy times time, and that happens to be h bar. So Planck's constant also happens to have this action unit. And so it turns out this will be important when trying to relate the Lagrangian mechanics to quantum mechanics. But we won't be dealing with that in this class because this is classical mechanics. Okay, so furthermore, in this historical context, Hamilton's principle. So Hamilton in the early 1800s, about 150 years after Principia, and 75 years after Euler, so we were dealing with Euler's equation last week, but about 75 years after Euler formulated his equation, he came up with this statement. Of all the possible paths along which a dynamical system may move from one point to another within a specified time interval, consistent with any constraints, the actual path followed is that which minimizes the time integral of the difference between the kinetic and potential energies. Okay, so that's equivalent to him saying like F equals ma in Newton's laws, say for Newton 2. In mathy terms, that means this delta from the integral of T1 to T2 of the difference of the kinetic energy minus the potential energy U integrated over time is equal to 0. So what he says that it's going to minimize the time. It turns out that by making this delta, this differential, it just has to be an extremum, but commonly in physics we'll be seeing that it's a minimum. And in fact, I think all of the problems that you'll see in this course, it will be a minimum. Okay, so basically what I'm trying to emphasize here is we've developed this mathematical tools that we saw works with geometry last week. And we saw that we could, maximize some area or, minimize some circumference or something like that. But it turns out that we've had those mathematical skills for geometry, and then Hamilton and Maupertuis have put these into physics context for trying to understand mechanics. And basically, with this statement here, he's basically equivalently said that like he's developed like this law saying equivalent to like F equals ma. It's basically saying like this, we're taking the delta of this is equal to 0. So it's kind of like I'm trying to stress that it's as important as that for Newtonian mechanics. Okay, so let's get into the derivation of this. I will briefly talk about this here. I'll get a little bit more into it in the lecture. But if we always think of the conservation of energy, E is equal to T plus U, then why are we actually using the Lagrangian? L is equal to T minus U, as Hamilton posed here, this T minus U. So we can use the energy of the system, though, to derive the Lagrangian as we go here. So the kinetic energy of a particle is, of course, T is equal to 1/2 mx dot squared. Where x is some function of our coordinates q. These can have any n number of coordinates. So in Cartesian, q1 would be, say, x, q2 would be y, q3 would be z, and also a function of t, time. We also have, for a conservative force, that the force is the negative of the gradient of this potential. Or written in terms of each coordinate, di u by di q k, where k is the coordinate number. So x, y, or z, for example, in Cartesian coordinates, or r theta phi in spherical polar coordinates. But it's conservative force, so that means that this potential doesn't change as a function of velocity. So that means di u by di qk dot is equal to 0. So if you think about this in terms of Cartesian coordinates, as I said, q1 would be x. So this would be di u by di x dot, or di u by di v in the x direction, is equal to 0. So that's our conservative force. And so that means that if we define this Lagrangian as L is equal to T minus U, then you put in this derivative of the Lagrangian. Well, you take the full differential d by dt of the partial derivative of dl di L by di qk dot minus di L by di qk is equal to 0. And that's it. So that's basically, if you look at all the definition of how these things are set up, we end up getting this equation that looks exactly like the Euler equation that we had last week. So we had set up for this geometry this constraint, or whatever, this condition for an extremum of this functional j. In order for that to have some extremum, we got this Euler equation. But it turns out if we set up this Lagrangian as t minus u, then we can just apply the same math to it, and it turns out that that is also going to be equal to 0, which means that we have this Euler equation, or we can call it the Euler-Lagrangian equation, Euler-Lagrange equation. Okay, so as I said, in terms of last chapter, we have the calculus of variations. We have this integral S is equal to the integral from t1 to t2 of this Lagrangian dt, and where this Lagrangian is t is L equals t minus u, and we call S the action. So we want to minimize the action, so that means that this delta S notation, if you remember that from last week, we have delta S is equal to delta of the integral from t1 to t2 L dt equals 0. So because of all the hard work that we put into last week, we know what this equation means. We know that we want to minimize this action, which means that we have this Lagrangian here that we want to find the condition for this action to be minimized, and that leads us to the Euler equation. But we apply this Euler equation directly to this Lagrangian t minus u, and that gets us the Euler-Lagrange equation that we have right here. So that's why we worked so hard last week on chapter 6, understanding this calculus of variations, because now we have the tools necessary to apply this to the simple case of this Lagrangian. And this is what we're going to be doing for the next 3.5 weeks, is just applying different Lagrangian, different physical problems to this, and getting the Euler-Lagrange equation from that. Okay, and then I'll finish off the lecture with an example by getting the motion of a pendulum, and we'll compare that to Newton's laws. All right, looking forward to see you there.